Okay, question 28. In the diagram shown, secants PQ and RS intersect at T, a point outside the circle with centre O. Determine the size of these angles RQP, RQP, and also ROP, ROP. When T is 36 and SRQ is 19, T is 36 and SRQ on there is 19. So to start off with, we've got almost everything we need. Well, we do have really everything we need to figure out the final angle within triangle TRQ, because we've got two of the angles already. So we know that for triangle TQR, it's going to be 180 minus your 36 minus your 19. Them two together make 55. 180 take 55 equals 125. And that will get us our angle on the outside over here. Obviously, to then end up getting the angle that we need, it's a straight line. So it's going to be 180 take 125 equals 55 degrees. You could have also had figured that out by just saying that angle is going to be the sum of the other two. Okay, so that one will be the solution for angle RQP. Now I'm going to just show it a little bit simpler. For the next one, we've got our arrow shape, and therefore the angle at the origin is going to be double the angle at the circumference. Therefore 55 times 2 is 110, and that equals angle ROP. And we're done for that one. Now, prove that when secants PQ and RS intersect at T, a point outside the circle with centre O, then angle T equals half angle ROP minus angle SOQ. Now, I was going to start writing this down the bottom here, but I think I might write it actually at the top, that way we can see the diagram. But I'll just be pausing to make sure I write things in and cover and go through them bit by bit. That way we can understand this as best as we can. So, to start off with, just delete things that we don't need, and then we'll start getting into it. So, first up, my first bit of script. So, like we saw in the previous question, we were actually able to figure out that PQR, so the angle in here, was actually going to be equal to, I'll just change the color, the sum of these two. That one there, and that one there. Okay, QRS. So that's where we start off. The next line that we'll have is PQR, angle PQR equals half of angle ROP. Now, this is not going to be surprising, given that the angle at PQR is, when you compare it to the angle at ROP, it's the theorem of the angle at the center is double that of the circumference. And obviously going inverse, one of them is going to be half of the other. So that one, hopefully not too bad. Next line will be the following. Now this next line, if you look at the triangles that I've made, it will make a bow tie. And then when I actually draw in, it is again saying that the angle at the center will be double the one at the circumference. So, and the inverse obviously would be that it's half. So angle QRS, the one highlighted in light blue, will be half the size, because that's the circumference, compared to the one pretty much on the inside of O there. Okay, that very little triangle that we've got in there. So that's just the bow tie theorem, I guess, that we've seen before. Informally, bow tie. So, now if we end up substituting in our definitions for our angles that we've just obtained from lines 1 and 2 into our original line there, this is what we'll get. And then if we take away the half SOQ, because we want to have T by itself on one side, we will end up getting angle T equals half angle ROP minus half angle SOQ. And of course we could just factorize that to make it angle T equals half angle ROP minus angle SOQ. And that's how you end up solving that one. Now, lastly, we have part C, which is determine the size of angle T when angle SOQ is 42 and ROP equals 82. So we're just going to put in the angles with what we've just already solved. And to be fair, even if you didn't solve it, you just put it in the formula that they just gave you up here. So angle T is going to equal half of your ROP minus your SOQ. Your ROP is 82 and your SOQ is 42. 82 take 42 is 40. Half of 40 is 20. That's what we do for that one right there.